In the first part of this lecture, you will learn the different types of interaction that can occur between gamma rays and matter. Then, we will focus on the most used technologies employed in gamma ray spectrometry, namely scintillation and semiconductor detectors. Let's start from the beginning. For gamma interaction with matter, the probability of a reaction to occur is related to two factors: the atomic number of the material and the energy of the impinging photon. The latter can be expressed as the product between the Planck constant h, which is equivalent approximately to 6.62 times 10 to the minus 34 meters squared times kilograms over second, and either the photon frequency nu, or the ratio between the speed of light c, that is about 300 million meters per second, and the photon wavelength lambda. The possible interactions are elastic scattering, photoelectric effect, Compton scattering, pair production, and photofission. Let's start with the first one. Also known as coherent or classical scattering, the elastic scattering is the process where the photon energy is lower than the binding energy of the electron in the atomic shells. Therefore, no energy will be transferred. Even though this event can happen during gamma or X-ray application, it is usually ignored. In the photoelectric effect, a photon interacts with an electron located in the atomic shell, completely transferring its momentum. The latter is ejected from the atom and interacts with the surrounding matter, losing all its energy in a relatively short path. This interaction is exceptional for gamma ray spectrometry, since it allows to completely collect the energy of the photon within the sensitive volume of the detector. The vacancy left behind will be filled by an outer shell electron, which will need to emit a photon to lower its energy to the appropriate level. This secondary photon emission is known as characteristic X-ray and is characteristic to each element. Compton scattering is an interaction in which a photon collides with a charged particle, usually electrons, and loses only a portion of its energy in the process. Following the event, the photon is deviated from its original path by an angle theta. When theta is close to 180 degrees, the maximum energy transferred is achieved, and the photon leaves with about 256 kilo-electron volts. The fact that the photon doesn't deposit all its energy in the matter in a single interaction makes the Compton scattering undesirable in the detection process. A peculiar way in which photons interact with matter is the pair production. During the interaction with an atomic nucleus, a photon can transform itself into an electron-positron pair. In this process, its energy is converted to the rest mass of the particles, following Einstein's equation E equals mc squared. For such reason, only photons with energy greater than the rest energy of the electron-positron pair, namely 1022 kilo-electron volts, undergo this process. The excess energy becomes kinetic energy for the two particles. Given its antiparticle nature, the positron will annihilate with an electron. This event causes the emission of two equally energetic photons, which, due to energy and momentum conservation, travel in opposite directions. Extremely energetic photons can directly interact with atomic nuclei, causing nuclear reactions. After the absorption of such photon, a nucleus goes into an excited state and immediately decays by emitting nucleons, such as neutrons, protons, or even alpha particles. This process is called photonuclear reaction or photodisintegration. A similar phenomenon is photofission. In this scenario, the excited nucleus undergoes nuclear fission, splitting itself into two smaller fragments. Regarding the most used technologies employed in gamma ray spectrometry, we can mention scintillation detectors, inorganic scintillation detectors, and semiconductor detectors. Scintillation detectors are a category of instruments that employs a scintillating material, capable of converting the energy of excited atomic states into optical photons. The light produced is guided to a photodetector. This device, usually a photomultiplier tube, can convert photons into an electric signal, which is then processed by an electronic chain and converted into a counting signal. To detect gamma rays, inorganic scintillation detectors are employed. These implement scintillating materials characterized by a high Z number, which significantly increases the probability of photoelectric events. Before proceeding, it is important to know the definition of a very crucial parameter for any detector, the energy resolution, which is defined as the ratio between the full width at half maximum of a peak and its corresponding energy. The two most important mentions here are sodium iodide and lanthanum bromide. Sodium iodide with thallium activation was the first ever employed scintillating material for gamma spectroscopy in 1948. Nevertheless, it still finds its use in modern gamma spectroscopy. It is characterized by an energy resolution of about 7% at 662 kilo-electron volts. Lanthanum bromide, with cerium activation, is a more modern and more accurate alternative to sodium iodide. It can provide an excellent resolution which goes at around 2.6% at 662 kilo-electron volts. Last but not least, semiconductor detectors, as the name suggests, employ semiconductor-type materials to convert the energy of incident particles into charge carriers, namely electron-hole pairs. These materials show an energy gap between valence and conduction band suitable for radiation detection purposes. This means that an impinging photon can promote a very large number of electrons to the conduction band by transferring them just a portion of its energy. For gamma ray detection, the most employed semiconductors are cadmium telluride and hyperpure germanium. Cadmium telluride is characterized by a large Z number which, as previously mentioned, enhances the probability of photoelectric effect. Moreover, cadmium telluride detectors are compact and can operate at room temperatures. Their typical resolution is about 6% at 122 kilo-electron volts. Hyperpure germanium crystals can be manufactured in significantly bigger shapes with respect to other semiconductors, thus ensuring the absorption of gamma particles up to a few mega-electron volts of energy. The main disadvantages lie in their high cost and necessity of cryogenic temperatures to operate, namely 77 Kelvin. Germanium detectors distinguish themselves for their outstanding resolution, which can be about 0.15% at 1332 kilo-electron volt.